Hey class, hopefully everyone is doing quite well on this wonderful day. This lab is our kind of video explainer for the ventilatory threshold and fuel utilization lab. Now, I think everyone knows the drill by now, include a short video or a bunch of pictures of you showcasing that you actually performed what I want you to perform, and then the worksheet at the back end. That, strangely enough, is not right here. So I'm going to take that off. The worksheet at the back end, turn in all of that type of stuff in. Just prove to me that you actually did this lab. Now, this lab is pretty interesting because there really isn't that much physical activity that you're actually going to be doing with this, and you actually need data from a previous lab in order to complete this. So the data you're going to need is what your VO2 max was from our VO2 max lab. Like ideally utilize the 1.5 mile run. That would probably be closest to the most accurate for this. However, if you made an argument for one of the other ones being a little bit more accurate, you can certainly use that VO2 max in this. So you're going to need that data. You're also going to need the Excel file that's given to you along with this sheet, and really from there you should be able to figure out just about everything. So let's go and get into this on just some background: VT anaerobic threshold and lactate. So whenever we're exercising, there comes a point where we increase in intensity, and then we start shifting from mostly aerobic metabolism to like oxidative phosphorylation, utilizing our mitochondria, to where we have such an immediate ATP need that we can no longer meet all of that ATP aerobically. So we start trying to meet our energy demands via anaerobic, like bioenergetic systems. So, like glycolysis, the phosphocreatine system, all of that type of stuff. And then we actually start breathing a little bit harder. So that's the ventilatory threshold. Whenever you notice that you're really hyperventilating quite hard, that would be the ventilatory threshold. And also there, we start noticing that if we're measuring blood lactate, we start noticing that there is an accumulation of lactate within the blood. So kind of in a way, if we had to parse these out as to what's actually happening first, we're probably going to hit our anaerobic threshold first, and then the ventilatory threshold and lactate threshold are probably happening approximately the same time. You could argue that the lactate threshold is going to occur a little bit faster because the lactate is being produced in the working musculature, and it's actually getting consumed in places like the liver and the heart and stuff like that. But I'm not going to test you on that because that's highly theoretical about what's going on there. We also have this other term, OBLA, or onset of blood lactate accumulation. Since this is online and I don't have my lactate measure given to all of you, where I'm going to prick your fingers and measure all that type of stuff, that's a little less important. However, I do want you to know that OBLA, it's typically whenever blood lactate goes above 4 millimoles, or it hits 4 millimoles per liter and then starts going up. Typically around rest, we're going to have around 1 millimole, and at max exercise, you could go up to 8, 9, 10, 12 in some cases. Typically, we would say that you're at your max of your aerobic system if your blood lactate is around 8 millimoles. So there's that. Read these definitions about, what the anaerobic threshold, lactate threshold, all of that type of stuff is. Here, this is showing somewhat of a pictorial representation, on these dual y-axes with ventilation liters per minute. And that's just not oxygen. That's just tons of stuff, everything really. And then over here, lactic acid, blood lactate accumulation, well, around that 4. Really, this graph isn't super great. It really starts inflecting up quite a bit around 4, give or take. It really doesn't start inflecting up around 2. However, I mean, it could certainly happen. I've measured numerous people that kind of go up in weird ways, but on average, right around 4 is really where it starts to kind of creep up slowly until a 4, and then like after the 4, it goes up to like 7, 8 pretty quick thereafter in oxygen consumption. So that's kind of what this is looking like more or less. So there's that, a little bit of an explanation there. Now, this fuel utilization, respiratory exchange ratio, all of these different types of things, and I'm going to get into the concept of what's called our fat max and our crossover point. So, with just a little bit of, balancing equations and, stoichiometry, I believe that's what it's called, we can figure out what fuel you're burning based upon how much CO2 is coming out of your mouth and how much O2 is going into your mouth. And if you just generally know a few of these things, like this one right here is palmitic acid. So there's a lot of carbons, it's a 16 carbon fatty acid. There's 32 H's, and then there's very little oxygens. So in order to oxidize a fat, the reason why it takes so much oxygen is because like there's basically no oxygen within that molecule. So if we balance this equation, a respiratory exchange ratio, or R, would be a 0.7. That would tell us that we're burning 100% fat. And here, burning 100% carbohydrates, C6H12O6, that's glucose. There's equal parts carbon and oxygen, so you don't need to consume near as much oxygen in order to fully oxidize that molecule. Now, granted, also a big part of why it takes so much oxygen to oxidize this palmitic fat, or like palmitic acid, this fatty acid, is because it is quite a bit of a larger molecule, of course, right? So there's some things there. Now, we're not going to be measuring these things. However, with this Excel document, I have put in a lot of time into tailoring like predictive equations that they're not going to be 100% right, but they're going to get you really darn close, like within the ballpark of what someone is actually burning. I'll show you that as that goes on. So here, this is just a figure I normally show, illustrating a few different things. That the respiratory exchange ratio, if it's lower, like it really only ranges from 0.7 to 1, and it can go over 1 at max exercise whenever we're hyperventilating. And it just kind of goes like fat to carbohydrates. And another thing here, kilocalories per liter. So this is one pretty curious thing that actually, in terms of getting energy out of these molecules, well, we're actually more efficient at getting energy out of carbohydrates than we are out of fats. Now, like, that doesn't really have much to say in terms of like how people can like be on a low carbohydrate ketogenic diet and like keto adapt or whatever. There are a lot of arguments for burning fat for fuel is a so-called cleaner fuel, because by burning it you frequently will make less reactive oxygen species, but carbohydrates are a little bit more efficient. And really, that's probably just a natural law of smaller things. We can just be a little bit more efficient with them than with larger things. So whenever you have like an excessive large like molecule, it's just harder to get everything off of it. So there's probably other various chemistry regions that are really beyond the scope of this class, but just wanted you to be aware of that. Next thing here, we have this idea of our crossover concept, where in terms of our VO2 max, at lower VO2 maxes, we're burning predominantly fat. At higher percentages of our VO2 max, we're burning more carbohydrates. So, as we're exercising more intensely, we actually need to get more efficient with, our utilization of fuel and all of that type of stuff, because at rest, we have so much fuel on us, we don't really, need that, right? Hopefully that makes sense. But we have this other concept over here of fat max. So this right here, pretty interesting. Um, you would think that whenever you're burning the most fat per minute would be whenever you're, burning only fat, essentially. However, that's not true. Something that you have to keep in mind, and you're going to have to figure this out for yourself, is that as we're burning, more fat calories, um, or sorry, as we're burning just more calories per minute whenever we, exercise at harder intensities, we can actually be burning a lower percentage of fat, but burning a higher absolute value of fat. So, here we have, like, say, over here, this, I believe, yeah, this is our, like, kind of respiratory exchange ratio going from like 8 to 1, or 0.8 to 1, sorry. And then, like, it's relatively low here, and our fat oxidation is pretty high. And then, like, here our fat max is actually closer to like a zero point 0.9 respiratory exchange ratio, which, if we were looking at this zero point 0.9, only 33% of the calories that you're burning per minute are coming from fat. The rest are coming from carbohydrate. But just because you're consuming so much more oxygen and you're burning so many more calories because you're working at a, sorry, right here, higher percentage of your VO2 max, well, then you're burning more fat calories there. So, we could utilize some of these equations to, maybe make it to where you burn the most fat that you possibly can, or say a client that you have burning the most fat that they possibly can during, an exercise bout. If you can only exercise for, I don't know, like 3 hours a week, right? Wouldn't you want to make it the most efficient exercise for whatever goals that you're trying to do, At least that's somewhat of an idea. All right, so for what we're going to be doing in lab, what you need, right, is some device to measure your speed. Ideally, a treadmill would work. Something that some of you might want to give a shot at. I haven't found any that I like, but if you could find some apps for your phone to like run with it, and yeah, there we go. To run with your phone on your side, and like it could tell you how many miles per hour that you're going if you wanted to. Now, if you can't do that, you're gonna have to be a little bit more, I guess, old school would be the term. Um, uh, Around a track, you can actually figure out quite a bit of things, right? So here, I just put this on here for you so you could effectively estimate how many miles per hour that you're actually like running. And say if you cover 100 meters in a minute, well, you're going something around 3.7 miles per hour. If you're doing one and like 125 meters, that if you cover 200 meters in a minute or so, then we're starting to go at like 7 miles per hour or whatever, and then 400 meters a minute, that's, starting to get right around 15, and stuff like that. So that would be a way to, figure that out if you're so inclined to do it that way. Honestly, if you have access to a treadmill, that would be the best way to do this. But I'm open to you being creative, figuring this type of stuff out. But here, um, the main things that you're going to be doing, you need to determine your ventilatory threshold, and we can do this just from this equation. So VT, this is liters per minute, and that's, going to be, it's going to be an oxygen, right? And all you really need to do with that would be to multiply it by your height in centimeters. Well, Sorry, you would really just do this equation. So 0.0024 multiplied by your height in centimeters, then subtract away this, your age, and then subtract away 2.43. Then after that, what I want you to do would be utilizing the Excel sheet, figure out what speed you need to run in order to reach your ventilatory threshold, and then you're going to need to try to maintain that for 3 minutes or so. And if you can maintain that for 3 minutes or so and you're breathing pretty hard, it's very likely actually your ventilatory threshold. If you're not breathing quite hard enough, then it under-predicted what your ventilatory threshold. If you can't even maintain this pace for 3 minutes, it over-predicted your ventilatory threshold. And I'm going to take you to the Excel sheet to kind of show you how to do that. But with this, something to keep in mind is that this equation, VT in liters per minute, that's absolute VO2, right? So you're going to need to be mindful that that's absolute, and a lot of the equations that we're going to use are going to be looking more at relative, right? So like I'll take you to there momentarily. I just wanted to cover a few of these other things. So answering this question, like, do you think it was accurate? Then I want you to utilizing the Excel document, tell me what your crossover point is, the point where you shift from burning mostly fats to mostly carbohydrates, and what your fat max is. So let's go and just check this out. So these equations right here. So these are the American College of Sports Medicine metabolic equations. And what I need to fill that out for you too, huh? What I did for you was I highlighted all of the yellow places. That's where you actually need to fill things out. We have this walking metabolic equation. However, most of you are not going to be walking. Most of you are going to be running. So that's really what I wanted to, highlight for us. Oop, right here. Let's take this away. I just had some values in there for us. All right. So let's look to see how this equation works, right? Body weight. This needs to be in pounds. So let's say that I weigh 163. That's a little bit below what I actually am, but that's cool. Let's say that I want to be jogging at 6 miles per hour. That would be a 10-minute mile. And notice here, you need to be over 5 miles per hour for this to work. And if we're doing this on a flat surface, 0% grade. If you want to take this and into onto a treadmill, you can certainly utilize that. So what this is telling us, this is predicting that if I'm running at a 10-minute mile, 6 miles per hour, I am at a VO2. This is our relative 35 milliliters of oxygen per kilogram body weight per minute, and my absolute VO2 is going to be at 2.6 or so, and I'm burning about 13-ish calories per minute. Probably want to go down here to look at these values because things are going to change a little bit. So there, 35. Here you would need to take your value from one of the previous labs, the VO2 max lab, and put this in. Let's say that your VO2 max is around I don't know, let's do some weird, 47. Why not? 47. So what this is telling you, 47, you are right at you're exercising about 75% of your VO2 max, 76 give or take. The percent of fuel that you're oxidizing is 80% or 80.5% carbohydrates, about 19 point whatever percent fats. Your respiratory exchange ratio should be around a 0.94, and then your kcals per liter is going to be right around this, and then your kilocalories per minute, it's going to be right around 13.1. So like I would go with that number rather than that number, if that makes sense. This one is probably more accurate because it's based upon the different fuels that you're oxidizing, whereas this, I'm just simply multiplying that by 5. And then carbohydrate calories and fat calories. That's how many calories that you're, burning per minute of all of these types of things. So, like you could. Oh, okay. Yes. Sorry. And if you want to figure out quite a bit more about this, you could just type in that you exercise for 5 minutes, and then it tells you like how many total carbohydrate calories you burned, how many total fat calories you burned, how many just total calories that you burned if you maintain this for so long, right? So what you're going to need to do, figure out what your ventilatory threshold is, based upon this here equation, that equation. Then you're going to have to go to here and plug in different things and make sure you're on the running tab, not the walk-in or the step-in. I'm just giving those to you so that you have them. Then you're going to have to plug in your weight, different speeds, and just figure out different things right here to try to get you near what that value is, and then it can be converted to the relative VO2. So hopefully that makes sense in what I'm actually trying to get out of you here. So there really isn't much better of a mathematical way other than plugging things in to this and then guess and check. Sorry that it's not any better than that, but it is what it is. But here, this is actually giving you like a fair bit of information, like how many calories you're burning per minute, how many, if you enter the amount of time, the total amount of calories, the fat calories, all of these different types of things. So hopefully that makes sense with all of this. Now let's look at some of the other questions that I want you to do. So you should be able to figure out your ventilatory threshold there. After that, what speed would you have to run to be at your ventilatory threshold? So that, just using Excel to guess and check within that. And then try to do this for 3 minutes and tell me if it's accurate. And again, how you're going to be able to assess that is if you can complete that miles per hour easily in 3 minutes, it's under predicting, so it's inaccurate. If you're able to do it but you're still breathing really hard, it's probably spot on. And if you can't complete it and it's and you're breathing just super crazy hard, then it's not right. And here, think about places where there could be inaccuracy in this prediction. And I mean, here this correlation is only like a 0.6, and a 1 correlation would be perfect. So this is saying that it's generally off by, a third of a liter of oxygen per minute, which is a fair bit actually. Next couple of things. This right here, you're going to have to write quite a bit on this. So utilizing the Excel file, explain in great detail what your crossover point is. So, like come over here and figure this out, that maybe, I don't know, 5.5, let's see, let's see, what you're going to be looking at for there is this respiratory exchange ratio, that type of stuff. So there, maybe it's, yeah, like it looks like my crossover point might actually not even be with running. So I might have to go back over here to walking. What did I say? I was 163. Let's 30, all that type of stuff, and 47. RER value right there. So well, so it kind of looks like, and this is going to be a bit inaccurate, um, but it looks like my crossover point is going to be just around me going probably around 4.5 miles per hour, something thereabout. So try to figure that out, and then also figure out the point at which you're burning the most fat calories per minute. And so that'll be what your fat max is. And then this one, and you can explain this any which way that you want to. How long would it take you to burn 100 calories of fat? So with here, like I'll show you how to do that one really quick. So let's say that I'm going at 7 miles per hour, and I'm looking down right here, total fat kcal. That, well, okay. Okay, so if I go with that speed, then here, 50 minutes. Here, let's see. Oh man, that's almost spot on. That's stellar. Okay, so if I go at 7 miles per hour for a full hour, then I'm going to burn almost exactly 100 calories from fat. Now, I'm going to burn a bunch of calories. Like, I don't even know if this would be sustainable for me to do. I might be able to do it, but probably not. Not super aerobically trained at the moment, but that's really about it. Hopefully this makes sense. I know that there was a lot going in with this, but just to recap everything that you need to do. Here, ventilatory threshold, figure that out from this equation. Then, after that, you're going to be utilizing the Excel document quite a bit, showing your work, figure out what speed you have to run to be at your ventilatory threshold, tell me if it's accurate or not, then start figuring out your crossover point and your fat max and all of those different types of things. And really, that's truthfully going to be about it. Let me know if you have any questions. I know that this is quite a bit in this lab, so good luck and let me know if you need any help. All right, thank you.